Hello and welcome to the makeup for Unit 4's activity, Ionic Puzzle activity. Using the various ion puzzle pieces, create 4 unique ionic formulas for each charge combination. Fill in the table as shown as you complete each combination by writing the cation and anion with their charges, the formula of the ionic compound with the correct subscripts, and draw one of them in the last column for each combo. Some pieces are blank. These are like wildcard pieces you can choose ions for, but do not write on the pieces. Some pieces are polyatomic ions. Avoid using these. Write the name of the ionic compound you draw. Remember, the net charge, total positives minus negatives, must be 0. Now, before starting, there are no wildcard pieces in the set that we have here today. There is one polyatomic ion that we must use based on the available pieces. And then in that last sentence where it says total positives minus negatives must be 0, it should be total positives plus negatives must be 0. Now what we have on this lab sheet and the table are various charge combinations. And we have 4 of 9 on the front side, plus and minus 1, plus and minus 2, plus and minus 3, plus 1 and minus 2, and then carrying over to the second side, plus 1 and minus 3, plus 2 minus 1, plus 2 minus 3, plus 3 minus 1, and finally plus 3 minus 2. Each of those charge combinations refer to the charges on the positive cation and then the negative anion. And it's that combination that you're using these puzzle pieces to reflect. Speaking of the puzzle pieces here, we have our set of positive cations. And our set of positive cations include sodium and potassium. Notice the little stick-out tab on each of those. Now that indicates a positive 1 charge for each stick-out tab that an ion has. We have 2 members of the alkali metal family for the 2 types of positive 1 cations. And then we have 3 representatives, 3 pieces, I should say, for 2 different elements, both in group 2, beryllium and magnesium. Notice that each one of those has 2 little stickouts, and therefore the ion is positive 2 in its charge. Lastly, for our positive 3 ions, we have aluminum and we have iron. Iron, a transition metal, has Roman numerals there. Now, you wouldn't be using the Roman numerals when you're writing cation symbols for these, nor would the Roman numeral come into the formula. The only place the Roman numeral would come into is in the name if you choose to write that one. But both of the aluminum and iron cations have a positive 3 total charge. Over on the negative anion side, we have chlorine and bromines anions, chloride and bromide. Notice how there's a little slot for each of those, each slot indicating a negative 1 charge on the negative cation. We have a member of group 6, oxygen's oxide ion. And notice that the 2 slots there represent a minus 2 charge. The other minus 2 ion was the polyatomic ion I mentioned earlier. It's sulfate, and its formula is SO4. The sulfate acts as a single entity, even though there are 1 plus 4 atoms for a total of 5 atoms. And because of the 2 slots, it is a negative 2 charged ion. Rounding off the minus 3 category are 2 elements from group 5, nitrogen and phosphorus. And then the ions there, nitride and phosphide. Remember, the name ending for the anions gets changed to IDE. The one exception would be the sulfate within this set. But with the 3 slots there, we have a minus 3 charge on each of these ions. Our task is to put the various combinations together and build these puzzle pieces. Noticing in the plus 1, minus 1 charge combination, we have one example already done, and that's going to be the potassium 1 plus ion. That's represented with this piece here, and we have the chloride 1 minus ion, represented by that piece there. Together, the formula they make is KCl, potassium chloride. Notice on the right side, we have in that last column the draw one. One of the 4 that you create, your choice, you're going to draw the shape of those pieces together, and then also naming them. as we name them, we name the first element, the cation. It's just the name of the element, that's all. But the anion's name must get that IDE suffix, so chlorine becomes chloride. The only exception to that would be with that sulfate piece, and its name is sulfate. So in addition to that potassium and chlorine example, let's look at another possible combination. We also had sodium, and we had bromide as the combination. So then if we take that sodium and that bromine, we can see how when the two pieces come together, you then end up with the combination that doesn't have any extra tabs or slots left over. In other words, you need one sodium and one bromide to make that perfect neutral formula. So 1 Na for every 1 Br. Let's go ahead and add that to our sheet for our ionic puzzle activity. So then in the +1 -1 combination, we have Na 1 plus, Br 1 minus. In employing the crisscross method, we'll take the ones and crisscross them over, and then we'll have subscripts for Na and Br, but we only put the subscripts in the formula. But, like mentioned in class, if the subscripts are 1, they're not written, but omitted. So our formula is simply NaBr. Now, as we put together these various charge combinations, we're not going to do every single one, but I will show for this initial charge combination 4 possible combinations that you're going to want to get. The only 4 that are there. And then after this +1 -1 charge combination, it's going to be up to you. So then, let's go back to potassium. Before with potassium, we put that with chloride in that first row. Now if we take potassium and we put it with bromide, we have a unique substance. And this one would be potassium bromide. We don't have to draw it because that +1 -1 combination was already drawn with KCl. So noting that, we go back to our chart. This time we used potassium. Although we used it already, we're using it again. And that's okay, because now with the potassium, we don't use chlorine, but we use bromine for the bromide. So we put K1 plus, Br1 minus, and then of course crisscrossing but not writing the ones gets us our formula, KBr. Now it's unique and distinct. What we've done is use the cation here and the anion for that other one and put them together to get a new formula. We're going to do that one more time. This time we're going to take the anion from that first row that was already done and the cation from that second row. So then we get our sodium with our chlorine. We put those together, seeing how they do the same thing and matching up, and now we have a new unique and distinct formula to write. From our cation, Na 1 plus, Cl 1 minus for the anion, we do our crisscross method and we have NaCl, the ones not written as they're omitted. And we've completed the combination of +1 and -1. Let's move on to the +2 -2 combination. +2 -2 combination, couple of options we have. We had magnesium as one of those pieces. We had oxygen as one of those pieces in the form of oxide. Those two come together quite nicely. One of each piece is all that's needed to get that complete formula. So let's go ahead and add that to our +2 -2 chart across that first row. So because it's 2 tabs on the magnesium and because magnesium is in group 2, it forms a 2+ charge on its ion. And oxygen with its 2 slots is a -2 ion. So we put O, 2-. And then doing the crisscross method, we'll see that the 2's would cancel each other out and we wouldn't write those 2's, nor would we write the 1's that they simplify to. So our formula is simply MgO. And we can elect to draw that one over here on the right. So we draw those pieces, carefully drawing them. labeling them as well. We have this one as our Mg, this one as our oxide, so our MgO, just like we see right here. And then naming it, we just simply take the name of the cation, magnesium, and the name of the anion, oxide. And we have that combination there. Another +2, -2 combination that we have uses the other cation, beryllium, and the polyatomic ion, sulfate. We can see, just like with the Mg and the O, the Be and this SO4 come together and fit quite nicely. One of each is needed. So then the beryllium is a +2, Be 2+, and the sulfate is a -2. Notice though, we have the formula for the sulfate. It's the SO4. We don't want to change anything about that. So we write SO4 and then 2-. Doing the crisscross method would have us simplify and reduce down those 2's to 1's, which we wouldn't write. So we simply have BeSO4. For the third and fourth rows, what you want to do is take the magnesium, combine it with the sulfate in those places there, write them again, and then you're going to get the formula together, MgSO4. And then take the beryllium with the oxide and then rewrite the Be and the O's ion formulas, and then together the formula BeO. We wouldn't have to name those other ones since we already took care of that with that first example. That same thing will apply to the rest of the charge combinations that you'll be completing here. Moving on to the +3 -3 charge combination. We had two elements to choose from for the +3 -3 charge combination. Aluminum was one of those metals. And for a -3 charge combination, we had nitrogen and phosphorus. I have selected nitride here. So then, with this, it's a matter of seeing how these two pieces come together just like the previous set did. And the 3 tabs of the aluminum fit into the 3 slots for the nitride. So we want to fill that in on our table under the +3 -3 combination. So we have Al 3+ and N 3-. Crisscross method has the 3's simplify out, so we don't write those 3's nor the simplified ones. So all we simply get is AlN. I'll draw one more for you guys here in this video. I'll go widthwise here. This is the stick outs or the tabs, so this one right here is the Al. These are the slots, so this piece here is the N. We just name it simply by looking at the names of each of those elements. We have aluminum nitride, and that's all we write for the name. Aluminum nitride. The other combination that we could possibly get before mixing has us look at the iron with the phosphorus, which is phosphide. Putting those together like that, we have that next combination. The Roman numeral 3 right there indicates a +3 charge. Now the iron's a transition metal, so that's actually a requirement when we have a transition metal to indicate what charge it has, since they can vary. But iron with the Roman numeral 3 means Fe 3+. And then our phosphide is a -3, so P 3- is what we write there. We put those together, we have Fe P as the ionic formula. The 3's reduced to 1's, and the 1's aren't written. Our next charge combination is +1 with -2. So here we have sodium to reflect our +1. We'll use oxide to reflect our -2. And in putting these together, we can see that one sodium's tab fits into one of the slots of total of 2 for the oxygen. So we're not done yet. There's still a -1 hanging out right there. That -1 attracts a second sodium atom, not just one, or sodium ion, not just one ion, but 2. So then when we transfer this into our +1 minus 2 combination, the sodium for its cation symbol is still simply Na1+, just like it was in the +1 minus 1 combination. Our oxide is O2-. But we've noticed that we needed 2 sodium cations in order to make this entire piece, as we put them together, have no tabs or slots left over. This is where the crisscross method starts being handy, and we can't reduce down those remaining values. So the 1 from the Na becomes the subscript for the O. Of course, we don't write that in the cation and the anion columns. The superscript value in the charge of 2 for the oxide becomes the subscript value for the Na in the formula. So we write Na2O. Don't write the 2 right next to the Na over here. Don't write the 1 next to the oxide right here. But in the formula, we have Na2O. Again, the 1 for the O is omitted. The other possible combination that we have for +1 and -2 of 4 total possible combinations involves sulfate and potassium. Now, the sulfate is -2, so the sulfate, like the oxide, will attract 2 +1 cations, and we end in a situation like this. And when we're going to fill this in on our chart, we write down the cation, K1+. We write down the anion, SO4, just like it was up here in the +2 -2 combination, SO4, 2-. And then we do our crisscross method. Here, though, we don't simplify. The 2 right here from the sulfate, not the 4, don't change the 4. The 2 crosses over and becomes the subscript for the potassium, so K2. The 1 becomes the subscript for the sulfate, but we don't write the 1s, so we simply write SO4. Notice I kept the 4 intact. Also notice I didn't draw that combination. You can go back if necessary, pause the video, and draw one or the other of those 2 possible combinations, or one you get in the 3rd row or the one you get for the 4th row. Remember, switch your partners, do-si-do. The Na with the SO4 could go in the 3rd row. The K with the O could go in that 4th row with their respective formulas. Flipping the page over, we'll notice that our next charge combination is +1 -3. So the +1 -3 combination, we can use phosphide. That's our -3 combination. Now this one has 3 spots where there's a -1 each, right there, and right there. And each of those 3 spots equally attracts a +1 cation, since we're doing the +1 -1 combination. So we have that. So we can see that 3 sodium ions are required to meet up with that phosphide ion. So putting that in, sodium is still just Na1+, as it was before. We don't change its cation symbol. The phosphide is still P3-, as it was before. We do our crisscross method. The 3 is the subscript for the Na. So the 3 crisscrosses, don't write it there. The 1 is the subscript for the P. We don't write that. So Na3P is the combination we have there. And we can see the name sodium phosphide, if you elect to name that, over here on the right after drawing that. So let me show that again for the drawing purposes. The other combinations that we have, we also have potassium that can meet up with that phosphide. And we have the nitride that can meet up with that potassium, and also the sodium we've already done. So get your 2nd, 3rd, and 4th row filled in with those other possible combinations. Our +2 -1 combination is next. Again, one example for that. +2 beryllium was one of those examples we had for our +2 combination. And a -2, we had oxide as a representative there. Those 2 come together Oops, I meant to grab a -1 combination, my apologies. So then chloride would fit there, chloride being a -1. And just like the -2 attracted 2 positive 1s, this +2 will attract 2 negative 1s. And hence, we have that right there. So Be with its 2+, Cl with its 1-, just like before. We do our crisscross method. The 2 is the subscript for the Cl. The 1, which we don't write, is the subscript for the Be. So we get BeCl2. The other elements that you could use to fill these in include magnesium and bromide. You can get a magnesium-bromide combination and then switch your partners do-si-do for the 3rd and the 4th rows there. A +2 -3 combination. And this one gets pretty complex with this +2 -3 combination. Magnesium, a +2, nitride, a -3. So we'll use those pieces there. But as I mentioned, with that complexity, we have a lot going on with this. So follow along carefully. So then, the negatives of the nitride attract the positives of the magnesium, and vice versa. But when we put one magnesium against one nitride, we can see that we have one -1 position left over. We can't take a +1 and fill it in that spot. We have to stick with magnesium. So all we need is another magnesium. So we put that other magnesium in there. Now we have the opposite situation. We have a situation where there's the +1 from the second magnesium left over. So what we need now is not a -1 to fill in that spot, but one of the negatives from the -3 nitride, a second one. So you can see how it's getting pretty long at this point. But now we have 2 negatives left over from that second nitride piece, and that finally ultimately gets filled in when a 3rd magnesium comes in and occupies that spot. For your chart, we just want to record that information. We have our +2 -3 charge combination. Our +2 is the magnesium 2+, our -3 is the nitride 3-. So Mg2+, N3-. So we write that in there. Mg2+, N3-. Now for our crisscross method here, then the 2 from the magnesium crisscrosses over and becomes the subscript for the nitrogen. The 3 for the nitrogen becomes the subscript for the magnesium. So we get Mg3N2. The other +2 that you're going to use is beryllium. That one can go with nitride as well. And then the other anion is phosphate. The beryllium can go with the phosphide, as can the magnesium. So fill in the 2nd, 3rd, and 4th row, draw one of them, and name it. And then we have our -3 -1 combination. The -3 -1 combination has us grab perhaps a phosphide. Nope, that's a -3, my apologies, a bromide. And then a +3, aluminum would work there, as would the iron. You'll do those ones as well. So then we can see that the +3 from the aluminum will attract 3 separate -1 bromides. So we fill that in, 1, 2, and 3. So we have ourselves 1 aluminum with the 3 bromides in that combination. So we write those down. So our +3, that's the aluminum, so Al, 3+, and our bromide, Br, 1-. The 3 becomes the subscript for the bromine. The 1 becomes the subscript for the aluminum, which is not written. So we're left with AlBr3. So aluminum bromide is what that one's going to be. Again, chlorine is the other -1 anion that you could use. Iron is the other positive 3 cation you can use. So get those combinations for the second, third, and fourth rows. Finally, a +3 -2 charge combination. That's essentially the mirror image to the +2 -3 combination. So let's use iron this time here for our positive 3 cation, and our -2 anion, let's use the more complicated sulfate, just so we can see it as an example. And that iron will attract that sulfate, and it will lock into that position right there. But we see we have a charge left over, so that sulfate will also go and attach right there, which brings in another iron cation. So it goes there. And then finally, our third sulfate. So we have that situation with these pieces. So then now there's no tabs or slots left over, so we have a complete structure, and that would be a good one to draw. When we're recording our cations and our anions, as we did before, we have our positive 3 iron cation. So we say Fe, 3+, and we had our SO4, 2-. Now, when we have a situation like this, we have to consider a polyatomic ion requiring more than one of them. So multiple SO4s. How many? Well, that's the 3 in the Fe. So we need 3 SO4s, and that becomes our subscript for the SO4. The 2 from the SO4 becomes the subscript for the Fe. So we write Fe, 2, and then SO4. But then we need more than one. Whenever you need more than one polyatomic ion, you got to wrap it up in parentheses and then put the subscript after the parentheses there. And we have the formula for iron sulfate. The other +3 that you're using is aluminum. The other -3 that you're using is oxide. Remember, whenever you're using sulfate there for one of those other 3 rows, you're going to have it wrapped in parentheses just like it is here with the subscript of 3. There are some questions at the bottom. So then a little bit of confusion here within number 3. If you just stop right there and I put that question mark there and then ignore the rest of it, then that'll make that one a bit clearer in what's being asked. Thank you for watching.